Welcome to today's video. Today we're going to talk about the notion of isometries, a very important notion as we will see later on because of the implication it has for physics. Alright, so a diffeomorphism going from n to n in a pseudo-Riemannian, could be Riemannian but also pseudo-Riemannian manifold, just metric, the manifold equipped with the metric, is an isometry if and only if it preserves the metric tensor G in the whole manifold. That is, the pullback of this diffeomorphism acting on the metric is equal to the metric everywhere. Now, a vector field K is an isometry if and only if the Lie derivative of the metric in the direction of the vector is 0. Alright? So, the metric, when you transport it through the flow of this vector, gives you a 0. Alright? Wonderful. So, the killing that condition here, it's equivalent to demanding this other condition, that the killing vector field satisfy this condition. Okay, and that is called the killing equation. Now, can we prove the killing equation? Well, let's see if we can. To prove the killing equation, we need to prove first another identity, and that identity is going to be related with the Lie derivative. Now, we had the Lie derivative here that we computed in previous videos for a vector field. We obtained this, and then computing the Lie derivative for the contraction of a vector in a one form, we obtained the Lie derivative of the one form in the direction of v, which is this. And then we talked about how to take the Lie derivative of higher order tensors that you can always do, taking Lie derivatives of contractions, and then writing everything in terms of Lie derivatives that you already know. We know that per contravariant index, you are a minus term that contracts the covariant index, or each of the covariant index with the partial derivative, and you add a term with a plus per covariant index where you contract the covariant index with the vector. You're taking the derivative with respect to it. So that's easy then, constructing the Lie derivative of for example, a twice covariant tensor. So you have the partial derivative term, and then you have a plus term per covariant index. One here, where the first index is the one that's contracted, and one here with the second index is the one that's contracted. Wonderful. So that's the Lie derivative of a twice covariant tensor. Now, we also know the covariant derivative has this expression here for a tensor that is twice covariant. All right. And we also know that if the connection is torsion-free, then the coefficients of the connection are symmetric in the two last indices. Wonderful. Now, what we want to prove, that we need to prove in order to prove the killing equation the way I'm going to do it, is show that in a coordinate basis and for a torsion-free connection, the Lie derivative of any twice covariant tensor can be written replacing the partial derivatives by covariant derivatives. That's kind of cool, isn't it? All right, let's get to it. So, step number one, let's expand these terms, the covariant derivatives, in terms of what we know the covariant derivative is for a tensor field, twice covariant, and a vector field. Like this. All that I did is substitute the covariant derivative of the twice covariant tensor here, and I've substituted the covariant derivative of the vector field here, the covariant derivative of the vector field here. All right. The next step is to separate the terms that actually give me the Lie derivative from there. Let's simplify here, grouping the terms as follows. Like that. So we have these three terms in red, I put them together here, and these three terms give me exactly the Lie derivative of the tensor, the twice covariant tensor in this case, and then all the other terms that I have, I actually separated them here. Alright, so let's take a look at these terms. One thing that I can quickly do with these terms is to have the dummy indices match. So I'm going to swap, for example, here, the rho and the sigma in both terms here. And then we realize this term and this term, well, they're the same, so they cancel. And now this term and this term, well, in a coordinate basis, remember that we have a symmetric connection, a torsion-free connection, so this thing, when I swap, it's exactly the same thing as this one. So this one cancels this one. And there you go. We started from this expression, and we ended up that the result is just the Lie derivative with respect to the direction of v of the tensor T, components mu nu. So we proved what we wanted to prove, that the Lie derivative, when we have a torsion-free connection in a coordinate basis, I can express as this expression. Wonderful, we proved it. Identity proved. I used a coordinate basis to make the calculations easier, but this identity is a tensorial identity. When we have a torsion-free connection, the Lie derivative of a tensor can be expressed, instead of writing the partial derivatives, I can write the covariant derivatives. This is true for any differentiable manifold, for any torsion-free connection. But now let's particularize to the metric tensor, and let's particularize to the connection, the Levi-Civita connection, the ones that compatible with the metric, and let's see what happens. So we have that for the derivative of the metric in the direction of some vector v. All right. But then, if the connection is compatible with the metric, we know.
Now, if the connection is this is the Levi-Civita connection, we know that nabla j is equal to 0.
And therefore, this is equal to 0. All right. So then we get that the Lie derivative, let me write it here, the Lie derivative in the direction of the vector v of the metric components mu nu are just g sigma nu nabla mu v sigma plus g mu sigma nabla nu v sigma. But then again, there's the metric we can use to lower the indices of the vector here. So what we get is that this Lie derivative is equal to nabla mu v nu, lowering the index, plus nabla nu v mu. Wonderful. So now you see that demanding that the Lie derivative along the direction of v it's equal to 0, which is the condition for a Killing vector field, we get in coordinates that this is the same as demanding that nabla mu v nu plus nabla nu v mu it's equal to 0, which is the Killing equation. There we go. Wonderful. So we obtained the Killing equation. And this is also a good practice exercise. This could have been another exercise that you could do. Why are isometries special, and how are they useful in physics? Well, isometries will allow us, when we have an isometry, they will allow us to define conserved quantities along geodesics. Let's take a look at it. If K is a Killing vector field and V is the tangent vector of a geodesic, then the quantity KB VB, which is the contraction of, so if I want to write in terms of the vector fields, it would be G AB KA VB. So this quantity is conserved along the geodesic. So this is kind of cool because it's physics, like those are conserved quantities. Like if you're free falling, for example, when we do relativity, we're going to be free falling following geodesics. And then suddenly, as we follow those geodesics, we may have conserved quantities that we can use to solve equations of motion without having to solve the geodesic equation or things like that, to simplify a lot of calculations. Those conserved quantities are quantities that we may want to associate to things that were related to angular momentum or perhaps energy or things like that. So finding conserved quantities along geodesics is very important. We will see how much we use that when we do orbital mechanics in general relativity. So let's prove it. A statement to prove. So in equation, let's write it in an equation. That is, right, the directional derivative in the direction of the geodesic, okay, of the quantity KB VB is 0. That's the claim. This quantity doesn't vary as I move along the geodesic. All right, so let's prove it. So the first thing we're going to do is use Leibniz rule in here. Let's start from here.
VA, nabla KB, VB.
Let's use Leibniz rule. So if we use it, we have the following. So VA, I'm going to take the VB out as well. VB, nabla A, KB. All right, that's the first term. KB, and now VA, nabla A, VB. Right. But we know the curve is a geodesic. Remember that being a geodesic means that we satisfy the geodesic equation.
Geodesic equation. What is the geodesic equation? Well, it tells me that the directional derivative of the velocity in the direction of the velocity is 0.
That's the geodesic equation. So that tells me that this term is 0, the fact that it's a geodesic. All right, so then we're left with this one. But we also know that this has to satisfy the Killing equation. So let's just write the Killing equation again. The Killing equation tells me nabla A KB equals minus nabla B KA, right? So I can write the following. This is equal to minus VA VB and then nabla B KA. But if you realize this expression and this expression are the same, only with a minus sign. This expression, I can swap the dummy indices A and B and I get exactly the same expression. So I get that this thing is equal this thing and these things are equal only with a minus sign. So this means that I can now go and say this is minus VA, nabla A, KB, VB. So something is equal to minus itself, therefore it has to be 0. And we proved it. All right, we proved that the quantity, the contraction of the tangent vector to the curve, to the geodesic, and the Killing vector field is the derivative in the direction of the curve is 0. So this is a conserved quantity along the geodesic. This is going to be extremely useful in the future. Well, here's an exercise for you, which is not too difficult to do, very similar to the kind of proofs that we've been doing. Prove that for a Killing vector field K, this is satisfied. The action of double covariant derivative is the Riemann contracted with the vector field with the index down. Okay? Remember, of course, that what I mean by this is just G, dA, Ka, right? Okay. Now also, once you've proven that, prove as well that the maximum possible number of isometries, so independent, the maximum possible number of independent Killing vector fields is given by this, where n is the dimension of the manifold. Now notice that in the case of 4-dimensional manifold, this number is 10. And 10 are the symmetries of, for example, flat spacetime, right? 10. How many isometries are there in spacetime? Well, 3 translations, 3 rotations, 3 boosts, and 1 time shift. 10. All right. Let's do an exercise where we actually compute Killing vector fields. Let's compute the Killing vector fields of Minkowski, shall we? That's a very simple exercise. Let's determine the Killing vectors of the Minkowski metric, which is this. Here's the line element with the coefficients of the metric being -1, 1, 1, 1. I made the speed of light equal to 1 here. It's called natural units. We will delve more into natural units when we do GR. All GR we're going to do in natural units, and we're going to learn how to use them. But indulge me for now to have this C equal 1 for the Minkowski metric. All right, so actually we can identify right away several killings just looking at it. Every time that you have a cyclic coordinate, what do I call a cyclic coordinate? The coefficients of the metric do not depend on the coordinate t. Oh, but that means that if I do translations in the coordinate t, the metric will be the same, because if I had a t in here, if I do translations with respect to t, t varies, and therefore the metric changes. But if t doesn't appear, then the metric doesn't change when I do a translation in time on the variable t, right? And that means that partial t is the direction of an isotropy. So I could identify right away cyclic coordinates with respect to which the metric coefficients have no dependence. In this case, all of them, t, x, y, and z. So allows me to t, x, y, and z allows me to identify. That means that the vectors partial t represent like 1, 0, 0, 0. Partial x, which I represent as 0, 1, 0, 0. Partial y, that I represent, let me just write this symbol, as 0, 0, 1, 0. And partial z, that I represent as 0, 0, 0, 1. This vector, right, in that case I'm using for this representation, the coordinates would be t, the first one, then x, then y, then z, all right? So like this. So partial t, partial x, partial y, and partial z are 4 Killing vectors, all right? So we could identify 4 already. Now, Minkowski is maximally symmetric. It has all the possible symmetries it can have, which we already discussed that for 4 dimensions, that's 10. Let's actually systematically find all the Killing vectors, and we'll see what they are. So for that, let's write the Killing equation. But I also wrote that the Christoffel symbols, in this case, the coefficients of the connection compatible with the metric, are 0. This is a flat metric, all right? And therefore, because this is 0, we know that we can write the covariant derivative as partial derivatives.
K alpha plus partial alpha K beta equals 0.
Right? Covariant derivatives are equal to partials if the Christoffel symbols are 0, if the coefficients of the connection are 0. In this case, the coefficient of the connection compatible with the metric. So what do we do with that? This is a first order differential equation that we can solve. And this is again, finding Killing fields is actually equivalent to solving differential equations. Now let's simplify this differential equation, actually taking another derivative. Ironically, if we take another derivative, if we take a partial mu, we get that this is
partial mu, partial beta, K alpha, plus partial mu, partial alpha, K beta equals 0.
Allows us to get all the possible equations in here and combine them in a particular way to cancel cross terms and get simple second order equations. Let's do that. So all that I did is get the Killing equation and cycle the labels. Just changing the name of the labels, cycling them. And doing that, that's it to simplify that so that I can cancel many terms. And you can tell I get this one, then I cycle the indices, and I cycle the indices, and I sum the first two and subtract the last one. It's a similar term with what we used to actually show computes the coefficients of the Levi-Civita connection, right? The Christoffel symbols. Now, we see, because the partial derivatives commute, these are coordinate bases, so we get that partial mu partial beta is the same as beta mu, so this one cancels with this one. Nice. And now we have beta alpha here, alpha beta here, this one cancels with this one. And this one are the same as well. So what we obtain here is twice partial mu partial alpha k beta equals 0. So we get a total of 10 equations per component of the killing vector. So this is what will allow us to solve for the killing vector fields. Let's do it. Let's write this equation just so to have them in front of our eyes. So if we write them, we obtain, I'm going to write them really fast, like that. So we get that all the second derivatives, all of them, of the components, have to be 0. All these equations have to be simultaneously 0. Well, that's easy. This is a differential equation that tells me that all the second derivatives are 0. So I can solve those equations. Those are simple. I know then that k beta it's equal to a beta, where a is a constant vector, plus b alpha beta x beta. All right, where x beta is this vector here. All right, so this is the vector field that simultaneously satisfies all these equations. So basically, affine linear combinations of the coordinates, only with one coordinate each. So the second derivative will always cancel them. All right, wonderful. Now, this is the general solution. We can find particular solutions as well. So before that, let's write, because the vector field really, I don't want the co-vector field. I want to have it with the index up. That's the vector field, right? So let's write the following. So the components of A beta are the t, the x, the y, and z components, and the matrix alpha beta crosses the components. And then, of course, the killing vector field will be the components contracted with the elements of the bases. Remember, the partial mu are the elements of the coordinate bases that we're using. What we can do is write this k mu as the raised version of the k beta, right? So remember that you raise the index with the metric. Here the metric is the flat metric. And that means I can substitute k beta for what I found the solutions of the killing equation were. And now I can build the vector fields just giving values to these coefficients. And we know that we have to find 10 of them. So let's find 10 independent ones by giving different values to the a's and the b's, the initial or the boundary conditions for those differential equations. Let's see. So let's do it in the form of a table. All right, first let me give the simple values. So I can give AT the value -1 and all the coefficients 0. All right, so looking at this, I know then that KT, the component T of the killing vector, will be -1 and all the others are 0. And cool, then I can compute the killing vector field using this expression that we found, right? Or in particular, this expression. And we only have KT component, but it's -1. The eta 0, 0, eta TT is -1 as well. So the killing vector field is partial T. Well, we already knew that existed. The first one that we're going to obtain are the partial T, partial X, partial Y, partial Z, which were the cyclic coordinates in this expression in coordinates of the metric. So let's find the second one, like this, and then you can tell we pick AX equals 1 and all the other coefficients equal to 0. Therefore, KX is equal to 1 and nothing else. And when we express it using this expression, right, we get that K is partial X, which is also what we already know because it's the cyclic coordinates. We can do the same. Now we do it with AY equals 1, all the others 0, AZ equals 1, all the others 0, and we would get the partial Y and partial Z. So here we would get also partial Y and partial Z to be killing vectors. All right, those we already know, we're the cyclic ones. Let's find more. All right, so now we can make the following choice. Let's make all the affine parts 0, so A alpha is equal to 0. And then let's make btx equals -1, bxt equals 1, and then make it 0 otherwise. So in that case, what do we get? We expand and we get the following, and we end up with the vectors x partial t plus t partial x, which is in components the xt vector, And this is the generator of boosts in the direction of x, which is amazing. So this tells you that the metric is invariant under boost in the direction of x. You can repeat the whole thing by changing the x here by a y, right? And then you get this one, and you change the x here by a z, and you get this one. These three Killing vector fields are the ones corresponding to the boosts along the three spatial directions of these current bases. All right. Now let's do finally another three independent ones by choosing this. We can choose now again all the components of A equal to 0, then bxy equals 1, byx equal -1, and all the other coefficients of B equals 0 otherwise, and then we compute the Killing vector field and we obtain this a 1, this a 1, this a 1, this a -1. What we obtain in the end is this vector field that I call K4 here, and this vector field that has x component equals to y and y component equals to -x is exactly the generator of rotations in the xy plane. And then, in a similar fashion, by swapping the spatial indices here, we get other two independent generator of rotations in the yz plane and in the xz plane. So these are the three generator of rotations, three generator of boosts, and the three generator of spatial translations here, and the generator of time translations. These are the 10 Killing vectors of the Minkowski spacetime. All right. Now that we've seen this, let's do a couple of differential geometry exercises that are interesting. And before doing that, let's delve a little bit more on the fully antisymmetric symbol, because we're going to use it for the next exercise. Let us revisit the Levi-Civita symbol. The Levi-Civita symbol is a symbol. I didn't call it a tensor because the exercise we're going to do is related with, is this a tensor, is this not? The Levi-Civita symbol is a symbol that in all bases and with indices up or down is a fully antisymmetric symbol, and the value of epsilon 1, 2, 3, 4, 5, 6, 7 all the way up to n indices is 1. And then that means this is a definition, and an equivalent definition, just to remind you, is 1 if the indices are an even permutation, the value of the indices is an even permutation of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. And -1 if it's an odd permutation of that sequence, and then 0 otherwise. Basically, there are repetitions in the value of the indices. Now, we also saw a way to check if a permutation is even or odd using a little graph theory trick. Now we're going to learn a little bit more about it. For example, we're going to learn some identities about it, and we're going to learn how to use it for determinants. Now, this is going to contain two parts. I'm going to give you some expressions that are super useful, and it's going to be an exercise for you to prove those expressions, because that's not difficult. And then I will do a problem that was actually a full assignment problem that I will solve completely about the fully antisymmetric symbol and the Kronecker delta. So that way we kind of split the weight in half. You have some practice for yourselves and then some solved exercises to see how we do things here. All right, first of all, let's talk about determinants. All right, so how do you compute determinants in index notation? So let M be a square n by n matrix of elements Mij, okay? The determinant of M is the contraction of the fully antisymmetric symbol, of the Levi-Civita symbol, with n indices and n copies of the matrix like that. It could be the one with the indices upstairs or the one with the subindices, all right? Both expressions give the same expression, give the same determinant. Now, an example in 2 by 2, you can tell. This is the matrix in 2 by 2, and now we say, okay, the determinant of M is the contraction like this. So let's expand all the terms, all the Einstein sums in here. And then we get, all right, so this guy is repeated indices. So this is 0, that doesn't contribute. 1, 2, that's an even permutation of 1, 2. So this is 1. Epsilon 2, 1, well, that's another permutation, just one permutation of the 1 and the 2. Okay, awesome. So this is -1. All right, and this is a repetition, so it's 0. Again, cancels. All right, so you see, we get that the determinant is M11, M22, minus M12, M21. M11, M22 minus M12, M21. So yes, indeed, it works for 2 by 2. Now, convince yourself that it works for any dimension. Do it for 3 by 3, and then check how it goes for 3 by 3 and see how it scales, and you will see that it happens. It makes sense, right? Because determinants are antisymmetric things. When you swap rows and columns and things like that. All right, wonderful. So we can also have a couple of identities involving determinants that I'm going to ask you to prove. These are the identities. So we have the M matrix as we had before. This identity is also true, in which I contract the fully antisymmetric symbol n copies of the matrix like this, and then I obtain the determinant times the fully antisymmetric symbol with the free labels, with the free indices. And here's the version where the two indices are downstairs. So the matrix, if the matrix elements are nij, this is the same version, the version of this equality. All right, this is something that you can prove. Here's another problem for you. What is the value? This one will give you the solution. Compute the contraction of the fully antisymmetric symbol with itself, the upstairs version, with when each index, ij, takes values from 1 to n. So here's two things. Each index takes values from 1 to n, and there are n of them. So what's the value of this? I'll give you a second to think about it. Okay, time. The value is n factorial. Now that you know the answer, can you think why? I'll give you a second to think about it. All right, so why is it n factorial? Well, you know that if you start combining the different values, all the ones that have repetitions are 0, because the fully antisymmetric symbol of two repeated indices is 0. And we know that then, of course, this can take all the possible permutations of these indices. Now, the permutations would be even or odd. But if it's even here, it's also even here because it's the same sequence. If it's odd here, it's also odd here because it's the same sequence. So it's either 1 times 1 or minus 1 times minus 1, every summand. So every summand is a 1. There are n factorial permutations of n elements, right? So this is why it's n factorial summands. All right, let's do a little bit more. The epsilon delta identities, they're ubiquitous. They appear everywhere in physics. Whether you're doing atomic physics or quantum optics or general relativity, you can benefit from the epsilon delta identities. All right, I wrote here the epsilon delta identities for 3 indices in the fully antisymmetric symbols, which is nice. It relates the contraction of the Levi-Civita symbols to the Kronecker delta. And here I wrote it kind of in general. So here I'm contracting the k first indices in both, and the second half are 3 indices, and this is what you get. You can write this contraction in terms of deltas, which is nice. Of course, this is an antisymmetrization, same as here, but now with more numbers, to antisymmetrize. Let's do an exercise and leave one for homework. Let's prove the following identity, that is a vector. In talking about vector calculus, let's talk about vectors in Rn. Let's prove the following identity for R3. Let's prove these identities. Of course, we need to remember that the cross product, so if I have the cross product of two vectors,
v cross w, and I want to have the component I, this is going to be the fully antisymmetric symbol I, jk, and then vj, wk.
Alright, so remember, this is the expression in components of the cross product, as we saw in the previous video, and also something that you can quickly check. Wonderful. So, knowing that, of course, and knowing the epsilon and delta identities, let's prove this expression. So step number 1, let me define two auxiliary vectors like this. So f, I call this vector here, and this vector b times c, I call it d, just for simplicity. So I compute d using this expression, I compute d, and then using this expression again, I compute f, right, where I call this vector d, of course, that I computed. I can substitute dk from this expression, and I get the following. I get this, right, just substituting d, and, well, just expanding. And the nice thing about it is that what I have here is an epsilon contracted with an epsilon, so I can use the epsilon delta identities. Now, keep an eye on how I use it, because, of course, depending on the indices being up or down, the deltas will have the indices up or down. Look at this expression and look at what I'm going to get, and try to see if you see the pattern, okay? Let's see. Let's apply the epsilon delta identities to this contraction. So you see, I applied exactly this expression, what I got here. The only difference is that the indices are sometimes up and sometimes down in the expression here as compared to this one. So the corresponding indices in the deltas would be up or down. One sanity check that you can do to make sure that you arrange the indices right is count the number and the value of the name of the superindices upstairs and downstairs on both sides, right? Here I get one superindex L and no others because K is a dummy index. And I get the L here, nice. And then I got 3 subindices, M, I, and J. M, I, and J. Okay, sanity check passed. This thing has the right number of indices. Again, look at this, look at that, and compare, please. Now, after having used the epsilon delta identities that you can use every time that you get fully antisymmetric symbols contracted, doesn't matter if it's upstairs or downstairs, okay, that's important, as long as you, the indices that you lower here and raise here, you lower and raise here as well. And what we are going to do now is play a little bit with this. All right, what did we do? This delta, with the I, the VI, the delta replaces a sum in here, so replace the I with an L, upstairs, nice. Now this other delta replaces the m with a j. M is going to be, the j is going to be downstairs now, so downstairs. Wonderful, and the c is the same. And for the second term, this delta replaces the j with an L, CL, and then this delta, the m with an I. There we go. And then we realize, what is this? This is the nth component of a vector like this. This is equal to, this is, remember, the inner product, the dot product AC, and this is the dot product AB. So, what we got here is the dot product AC multiplying the vector B minus the dot product AB multiplying the vector C component L. And we proved what we wanted to prove, which is this identity. Wonderful. Now, here's another identity for you to do for homework. Let me give it to you. This one you can use to practice. Also using the epsilon delta identities, compute prove this expression here. This could be nice practice with indices and things like this. All right, so now that we've seen this, let's do a little bit of practice. Here's an exercise that was part of an assignment of differential geometry in previous courses. I think it's a pretty cute exercise. All right, we're gonna end the video with solving this problem. Now, this problem has three parts. First of all, we're going to talk about the delta, about the identity in a way, and the Levi-Civita symbol. These are special because these symbols are defined to have the same value, so the components of these symbols have the same value in all bases. If I change bases, well, they have the same value. So the suspicion is that those things are not tensors. Remember, for something to be a tensor, for an object PAB to be a tensor, I need that under changes of bases, P prime AB would be equal to AD BC PDC, right? They need to change with 1 lambda per covariant index. And if the components don't change at all in any change of basis, suspicion is that maybe they're not tensors. So let's check. All right, let's erase this. And let's deal with the delta first. So the delta, it's funny because the delta, remember, delta AB, it's equal to 1 when A equals B and 0 otherwise, okay? And that's true regardless of the bases. It should be the same in all bases. It's just 1s and 0s in all bases. Those are the components. Is that a tensor? Well, let's see. If it were a tensor, then delta prime AB should be equal to lambda, as I wrote before. Let's see. Let's gonna have an A down, and then a C here, and a lambda tilde, and then I'm gonna have a B here, and a D here, okay? And then delta C, D. All right, so this is if delta were a tensor, okay? Now we know that delta is actually these values no matter the basis, so we have to prove whether at the same time this thing can have the same values in all bases and also satisfy that they transform like that and they change the bases. But let's see if it does. Well, that's actually pretty easy because this thing, this delta, I can use this delta to change one index here. So let me write the next line, AB equals, and then lambda AC, and I use the delta here to change that B by a C. Lambda tilde BC. All right. But now I also know that this lambda is the inverse transpose of this lambda. So first of all, let me take a transpose. So if I do lambda AC and then lambda tilde B, let me just write inverse transpose BC. So I just substitute lambda tilde for what it is. What I'm going to do now is I'm going to do a double transpose. So doing nothing. I'm going to do lambda AC, and then here I swap the indices, which takes care of that transpose. Lambda minus 1, now indices swapped, CB. Oh, look at that, this is a matrix product, but it's a matrix product of a matrix with its inverse. What is the result of a matrix product of a matrix with its inverse? The identity. This is literally delta AB. So indeed, delta AB. Oh, nice. So yes, it has exactly the same form. Delta prime happens to be delta AB. For any change of basis, the delta is the same. And it's this value here. This has this value here. So we proved, yes, the identity AB is a tensor. And in fact, you know that as a matrix, the identity is the only matrix that is the same in all bases because the changes of bases matrix commute with the identity. So yes, of course, the identity is a tensor and has the same entry, the same components in all bases. All right, so the delta passes the test. How about the epsilon, the fully antisymmetric symbol? Let's see it. Well, if the Levi-Civita symbol were a tensor, it had to transform like this. However, we learned in the identities that we saw before, this thing has a determinant in it. Remember, if we contract the fully antisymmetric symbol with n copies of the matrix, we get the identities related to the determinant. In particular, we use one of the identities to have this. So we see this is one of the identities we saw. The contraction of all the upper indices with the fully antisymmetric symbol gives me the determinant of the change of matrix basis times the fully antisymmetric symbol, which of course is different from the fully antisymmetric symbol because of this determinant factor, and therefore we don't have the same as we go with the delta. Both the epsilon and the delta are defined as having the same components, same entries in all bases, but if it were a tensor, it would have to satisfy this, and we see that it can satisfy at the same time the definition and this change of basis, because under this alleged change of basis it would change, and we know that the definition tells me that it doesn't change. Therefore, the fully antisymmetric symbol, the Levi-Civita symbol, is not a tensor. Proven. Now, here's an interesting part C. Show that the Levi-Civita tensor, I wrote pseudo-tensor, is often called tensor or tensor density, which is the object whose components are, you see, a different epsilon, different style of epsilon, a1, an. I add the square root of the determinant, absolute value, the determinant of the metric, this G is the metric, multiplied by the Levi-Civita symbol. So I upgrade the Levi-Civita symbol multiplying by the square root of the determinant of the matrix. Prove that that is a pseudo-tensor. Now, what is a pseudo-tensor? A pseudo-tensor transforms like a tensor, except for perhaps a sign of the determinant of the change of matrix, or change of basis matrix. Let me show you. So if PAB is a twice covariant pseudo-tensor, it transforms with two lambdas, as it should. If it were a tensor, it would be just that. But it has also a term that is the sign of the determinant of the change of basis. Those things are called pseudo-tensors. And they're related with something called tensor densities. Now, if you ever see field theory, you will learn what a what a tensor density is. Tensor density is something, an object that when you integrate over the volume, over a volume, it becomes a tensor. And then therefore the word density is a tensor per unit volume in a way. But this is more advanced, well, slightly more advanced than the course. It's outside of what we're going to see by a tiny bit. Not much, to be honest. But at least, I mean, here's the definition of pseudo-tensor. They transform like a tensor, but only adding the sign of the determinant of the change of basis matrix. That's kind of cool though. That thing that is not a tensor at all, suddenly if I add the square root of the determinant of the metric, what? Then suddenly this thing becomes a pseudo-tensor. Interesting. Let's see it. Alright, let's understand how the metric changes and the changes of bases. And the change of bases, the metric, which is a 0-2 tensor, transforms with two lambdas, as it should. Now, this thing is a kind of a matrix product. We can write as a matrix product as follows. So this thing is lambda B1, A1, G, A1, and then I have this one here. To have it as a A2, to have it as a matrix product, let me do a transpose here. So I have transpose A2, B2, and now it's in the canon form of a matrix product, right? So this thing is the matrix product. If you want, let me write as a matrix product. G prime as a matrix, it's equal to lambda G lambda transpose. As it should, because that's what happens with symmetric tensors that are twice covariant. You may have seen that in algebra, I'm not sure. You may have seen it in algebra when you were studying quadratic forms. I don't know. Maybe you've seen it, maybe not. But this is how it transforms. That's, well, the proof is here. All right? But then that means that the determinant of the metric transforms as follows. We use the properties of the determinant. This thing implies that the determinant of the transformed metric, it's equal, using the properties of the determinant of the product is the product of determinants, and also that the determinant of lambda is equal to the determinant of lambda transpose. We get that this is equal to the determinant of lambda square determinant of G. All right. So the determinant and the change of basis transforms, the determinant of the metric and the change of basis transforms with the square of the determinant of the change of basis matrix. All right, now that we've established this, let's write two things. Let's write how the Levi-Civita tensor transforms under change of basis, so what it really does, and then we'll write what it should do if it were a pseudo-tensor. And then we'll compare if what it does is the same as what it should do. Let's see, let's do first what it does.
So under change of basis, indeed, so we have the Levi-Civita pseudo-tensor A1, AN, the prime should be equal to the square root of the determinant of G prime, and then the Levi-Civita symbol prime, A1, AN.
But I know how the Levi-Civita symbol changes. It doesn't, by definition, it's the same in all bases, and how the determinant of the metric changes, which is this thing. So this is equal to the square root of the determinant of lambda squared, absolute value, determinant of G. All right, and then just epsilon A1, AN, because this thing is the same in both bases. All right, so this is how the Levi-Civita pseudo-tensor does transform. Actually, let me write it.
What it does under change of basis. Okay, now, to be a pseudo-tensor, it should do this.
Let's see. Like this. So epsilon prime, the pseudo-tensor, has to be equal to the sign of the determinant of the transformation, because it's the pseudo-tensor transformation, times n lambdas, n changes of basis matrices. Okay? And this is before the change of basis, the Levi-Civita tensor. Now I can write this in terms of the determinant of the metric and the Levi-Civita symbol. Things to realize. Oh, look at this thing. Whoa. This thing. This is again the same kind of identity we had from before. This thing is one of the determinant identities that we saw. Let's substitute it. So you see, this identity, this thing, you contract the lower indices with the upper indices of the matrices and copies of the matrices, so I get the determinant times the fully antisymmetric symbol with the indices that are free. So this object. This thing is this thing, as we saw in the identities right before. Okay, so now we're gonna use the following. That, you see, for a being a real number, I can put it inside the square root, put in the square, but of course, if it's negative, the negative stays out. So this identity is how you put things into square roots. The sine of a, square root of a squared b. Now we can apply it here and have this determinant enter the square root. And let's do it. So the tensor a1, an, it's equal to, and then I write the sign that I had from before, sine of determinant of lambda, and then I put the determinant inside, so that's another sign of the determinant of lambda, right? And then I get the square root. Let me put the square root in here, and with the square root I get the determinant of lambda squared and the determinant of the metric absolute value, and then the fully antisymmetric symbol, b1, bn. Now, of course, the product of the sign of two sides of the same thing, the sines of squared, sine function squared, is 1. So what we found is that the transformation is square root of the square of the determinant of lambda squared, so just the square of the determinant of lambda, sorry, absolute value of the determinant of the metric tensor, and then the fully antisymmetric symbol b1, bn. So this is what it should do. What it should do is this under the transformation. All right, so we compare what it should do with what it actually does. Look at that. Look at this. Isn't that beautiful? Ain't it amazing? Look at that. What it does and what it should do is the same. So indeed, epsilon, the Levi-Civita pseudo-tensor, is a pseudo-tensor or a tensor density. Wonderful, proven. All right, well, this is all that I wanted to show you today. With this, actually, we finished the block on differential geometry. Now, finally, in the next video, we're gonna begin with general relativity, and we're gonna begin with the postulates of general relativity, analogously to what we did with special relativity. I'll see you there, and until then, take care.